morning and hope you're enjoying the Big Easy. So we talked about this previously, about the Ka and Kb and how they are special K values. They work exactly like Kq. So Ka is simply products over reactants. Don't forget that the concentration of the undissociated molecules has a number. Okay? So what we're going to do today is we're going to take this concept and we're going to start adding numbers using Rice tables. Do you have any questions before we jump in? All right, so once again, so I mentioned that there's this really cool relationship that if you look at the Ka values and you look at the Kb values and you plug in like the H3O plus and OH minus, if you make B like NH3 and HA is NH4 plus and NH4 plus, and then B, when you put these two together, there's a better treatment on the black line. You get the Ka times the Kb equals the Kw. Now, just like we have a pH and a pOH, there's also a pKa and a pKb. Use the exact same logarithm math. If we take the logarithm of the Ka and the logarithm of the Kb and the logarithm of the Kw, again, at 273, Kw is 10 to the negative 14. It changes when the temperature changes, and that's a whole thing we're going to be talking about like later on this week. So take a logarithm of this, you get pKa, logarithm of this, pKa, logarithm of this, or sorry, negative logarithms, you get 14. So just like the pH plus the pOH is 14, the pKa plus the pKb is 14. And just like the hydronium concentration times the hydroxide concentration is 10 to the negative 14, the K of the weak acid and the Kb of its conjugate are 10 to the negative 14. Okay? So here's the important thing. Just like before, if you have H3O concentration, you have all four. You have the hydroxide, the pH, and the pOH. If you have any of those four things, you have all of them. pH and pKb work exactly the same way. If you have anything, the Ka, the Kb, the pKa, or the pKb, you have all of them. And more importantly, this is tested, I would say every year, they want you to know that if you are looking for the K of a conjugate base, you can just divide 10 to the negative 14 over the K of the acid, and you'll have the K of the conjugate base. Or if you're looking for the K of an acid, and its conjugate base K is given, divide 10 to the negative 14 divided by what you have, and you're going to get what you don't have. And the reason that comes up a lot is the question will be, or what usually comes up, is they will give you a question that clearly needs a Ka, but they won't give you the Ka. They'll give you the Kb of its anion. For instance, let's say you're going to do a Rice table, and you got the H, again, everyone's favorite HA is acetic acid, and that's going to be in equilibrium with H plus C2, H3, O2, this is the A minus, and this is the H plus. Okay, so then you're going to do a Rice table, and you're going to be like RICE, and you're going to basically take the equilibrium values, and you're going to go Ka equals the H plus concentration and the C2 H3O2 concentration over HC2 H3O2, and you're like, okay, I'm ready to do the math. What's the Ka? And you look at it, and it didn't give you the Ka. It gave you the Kb. And you're like, well, crap. I don't know what to do now because I need a Ka. Well, what it did is it's going to give you a Kb, and the Kb is going to be something like 1.5 times 10 to the negative 9. And you're like, all right, I can use that to get the Ka. I can say, all right, and by the way, and it's going to say the Kb. It's not going to say the Kb of this anion. It's going to say the Kb of NaC2H3O2, because basically it's this. Okay, it's going to say the Kb of this salt, the conjugate, or they won't say it's a conjugate base. They're going to say the Kb of this salt is this, and you're like, why are they giving me a Kb when I need a Ka? Aha! I just take my 10 to the negative 14, divide by the KB, and I have my Ka. This gets tested, this very skill gets tested about every other year. So any other time, could show up. All right, are you comfortable with this idea? Okay, the most important thing about acid and base is if you have anything of the H3O, OH, pH, pKa, or POH, you have them all. If you have anything of the Ka, Kb, pKa, pKb, you have them all. The trick is looking for the conjugates. C2H3O2, oh, that's A minus. That's the conjugate of that weak acid. Maybe it's going to do, they'll say the Kb of NaF. Maybe they won't even use Na. Maybe they'll say like Kf. The Kb of Kf is some ridiculously small value, 10 to the negative 10. So, oh, that means that the Ka of HF is 10 to the negative 14 over 10 to the negative 10. Capiche? Okay. All right, so there's that. So let's go ahead and get to the black lines. And black lines. No, black lines, here we go. All right, so, whoop. So again, strong acids, one-way street, doesn't go back. There's our a bunch of weak, strong, weak. Again, 6 strong acids. Memorize them. They're hydrochloric, hydrobromic, hydroiodic, but not hydrofluoric. And then nitric, sulfuric, and perchloric. Again, you wrote these before. Nitric is HNO3. Sulfuric is H2SO4. And perchloric is HClO4. Sometimes they used to include chloric acid because it's close. But okay, so here is the treatment, which I think is pretty cool right here. Yeah. So if you look at this relationship, NH3 here is a base because it's going to accept a proton from water. Again, there's multiple definitions for acid and base. We only care about what's called the Bronsted-Lowry definition. Bases take, acids donate. So takes the proton, we have an H4OH. So the Kb is this concentration. So again, products over reactants. There's that. And then you look at the acidic solution. This is the conjugate of that weak base. There's the weak base, there's its conjugate. And the acidic solution is just the opposite. But in this case, the conjugate acid is then attacking, or is then donating a proton to water, forming the base. Again, an acid's conjugate is its base, and there's H3O plus. And then you look at these two things, and you get this. That cancels out, and you get OH times hydronium, which we know to be 10 to the negative 14. Cool. All right, good. Moving right along. Okay, here we go. An acid dissolved in water, the pKb value associated with this conjugate base was found to be 15.5 at 25 degrees. It's always been 25 degrees. They will never give you a calculation that isn't at 25 degrees. All they will do will say, what happens if it gets warmer? Which we'll talk about later. What is the pKa value for the acid? Is the solution acidic or basic? Is the conjugate base a stronger or weaker base than water? So go ahead and answer these questions on your notes and then show your neighbor and see if you have a pretty good idea what's going on. And by the way, I'm not going to do the math. You do the math. I'm going to wait for the calculation screen. Oh, don't see that. It's not there. You guys all know how to do a negative logarithm, right? Just do the raised to the negative, whatever that thing is. if you want to borrow one of the white calculators, which is perfectly fine. Better to buy your own, but whatever. Okay. How did you get to pKa? How did you get part A?
It's like 10 to the negative 14 divided by 13.5.
But this is a pKb.
Oh, it's a PK.
Ooh, yeah. So the relationship is pKa plus pKb equals 14. So this is pKa is simply 14 minus 15.5. It's just that easy. Don't have to do any wonky exponents just yet. We will foresee. There we go. So pKa is negative 1.5. Is a solution acidic or basic? Well, we can now do our 10 to the whatever until we can see pKa's and pKb's, just like pH's and pOH's. So now let's go ahead and just do our 10 to the whatever. So 10, no idea. 10 to the negative 1.5 is going to give us our Ka. And 10 to the 15.5. Yeah, sorry, this is positive 1.5. It's going to give us our Kb. So what's our Ka? How much?
31.6.
Yeah, it's massive. It's just enormous. So is the solution acidic? Oh, yes. This is a very big Ka. Because again, realize what Ka means. Ka is the H plus concentration over, A minus, and the A minus concentration over the HA. So if you have a Ka that is larger than 1, you have a massive numerator in the Ka value. That means you've got a lot of protons. Cool? Do you understand? You understand what I'm saying? This is super important. The Ka, yes?
How did we get Ka? How did we get 36?
Okay, so once we found the pKa to be negative 1.5, we unlogarithmed it, because to unlogarithm, you go 10 to the negative pKa. Just like to unlogarithm your H3O concentration, it's 10 to the negative pH. So you anti-logarithmed it. I always do 10 to the negative whatever. Okay, so 10 to the negative pKa would be 10 to the negative 1.5. Is that clear?
And then you multiply the pK and the pKb.
If you want to.
Or
I mean, we're not actually looking for the pKb, but we could, or we're not looking for the Kb. We could find it if you wanted to. I mean, and we could have done this another way. We could have gone, the Kb is 10 to the negative 15.5. That would give us the Kb. Then we could say, oh, and then the Ka is 10 to the negative 14 over whatever that Kb was. Should probably use different colors, but get the idea? So, is this a solution acidic or basic? It's crazy acidic. That's an enormous Ka with a huge numerator of protons and anions. Is the conjugate base a stronger or weaker base than water? Can I erase this? Actually, you know what? I'm not going to erase it. I'm going to use a different color. we will use blue. Okay, so it's basically saying, is the conjugate base of this acid. So if the Ka we solve to be 36.1, now we can solve for the Kb of its conjugate. So far, so good. So again, the acid is very robust, which means its conjugate is going to be very feeble. And it's just going to be 10 to the negative 14 over that same 36.1, which is going to be teeny tiny. We have a number? I don't know what this is. Could be 10 to the negative 15 something. It's going to be that, actually.
2.77 times 10 to the negative 16.
Negative 16. So that is an exceptionally feeble weak base. So in the question is, you see why this is an exceptionally feeble weak base? Is the conjugate base a stronger or weaker base than water? Neutral water has a Kb of what? 7. Oh, 10 to the negative 7. Yeah. So neutral water has a Kb of 10 to the negative 7. Neutral water has a Ka of 10 to the negative 7. Neutral water has a Kb of 7. Neutral water has a pKa of 7, pKb of 7. So this is clearly less than 10 to the negative. Clearly less than 10 to the negative 7. So its conjugate is much weaker a base than water. How are we doing? Let's do another one. Boop, 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 boop. Okay. Water. Conjugate base is the weaker base than water. Water and the conjugate base compete for protons, and water wins every time. That's just for that particular acid, which is kind of funny. Find the pH. Ooh, okay, here we go. This is going to require some really cool calculations. Find the pH of a 2.5 molar solution of HF. There's the pKa. Follow me to the rice table. I'm gonna make it. I gotta rewrite the whole thing. Okay, so our reaction is HF is in equilibrium with H plus F minus. And when it says, what is the pH? It's looking for this number that we can then take the negative logarithm of. Because this is going to be the H3O plus concentration. So when it says, what is the pH of this solution? What it's really asking is, once this solution gets to equilibrium, maybe it's there, maybe it isn't. When it's at equilibrium, what is the hydronium ion concentration? Ready? Questions before we start? Yes?
Why do we take the negative logarithm?
Because the negative logarithm of the hydronium is pH.
Okay.
So when you hear P, think negative logarithm. pH is the negative logarithm of the hydronium concentration. POH is a negative logarithm of the hydroxide concentration. Cool. Other questions? Okay. So now look at the information we have. We have a 2.5 molar solution of HF, which is massively concentrated, but it doesn't really matter at this point. So we are starting with 2.5 molar HF. And we're pretending that at the moment we make a solution, it's only HF, and then it creates the protons and the anions. Rice. This is the initial. And then the change is where we use our X's. What am I going to put in the change for HF?
Negative X.
Negative X. And the change for H plus?
X.
Plus X. And the change for F minus?
Plus X.
Plus X. Are you with me so far? And then once again, the equilibrium is going to be this and this put together. It's going to be the 2.5 minus x. This is going to be x, and this is going to be x. And this is where we say, because we don't want to do the quadratic, that 2.5 minus x is basically 2.5 because the x change is going to be much less than 1. Actually, it's much less than the number of significant digits, which is given, which is 0.0. And this again, this comes from the fact that HF is a weak acid. Again, you never have to use a quadratic. Haven't had to since about 2004. All right, next. What am I going to do with all this information? I'm sorry?
Find the pH.
Yes, but first I have to do something.
Put it in the formula.
The equilibrium expression, yeah, put it into the, again, we call this the equilibrium expression. And you really need to use the lingo. Because if you don't, then you basically give the AP grader a reason not to give you points. So put in the equilibrium expression, which is going to be, once again, H plus concentration, F minus concentration, over HF. Do we have the Ka for this equilibrium expression?
Yeah.
It's not given explicitly, but we have it, because what it does give us is the pKa. So let's use the pKa to get the Ka. Do you know how to do that? Go for it. So calculate the Ka. I know it's on the board. Get the practice of calculating it. See if you get the same thing you are. Wish I could do these one slide at a time. I don't want this there. What do we get? We get our 10 to the whatever.
Yeah.
4 times 10 to the negative 4.
That equals all this stuff. So, x, H2O is going to be x, F is going to be x, 2.5 is going to be HF, so this is x squared over 2.5. And now we can solve for x, which is both the H plus concentration and the F minus concentration. You figure out what that is, please.
0.043.
You already got it? Okay. Wait for our best to get it. Plus there's something I want there. We don't need to use a trick, actually.
What'd you get, check?
0.043.
All right. So you've got the x as what?
0.043.
4.30 times 10 to the
Second.
negative 2. All right, cool. So that is the hydronium ion concentration. If we want the pH, what do I do?
Take the negative logarithm.
Take the negative logarithm of it. So go ahead and do that. Take the negative logarithm of 4.30 times 10 to the negative 2, and that will be our pH.
Yeah.
Again, HF is a very robust weak acid. So what's my pH?
1.37.
1.37. And again, I'm not going to worry about the significant digits, but okay. So see, we've matched what the author got, did the ice diagram, found, didn't solve it for you. And whatever. Okay. Anyway, that's right. That's all right. Okay. Are you comfortable with this? Okay. Find the pH using calculated value, not important. Find, okay, percent ionization. Okay. So percent ionization is something new, and it's something really strange. Percent ionization is simply how many ions you get for how many undisassociated molecules you get. I haven't seen it. Honestly, it's in your homework, but I haven't seen it tested in a very long time. But it is still in the curriculum. So percent ionization is simply the A minus concentration over the HA concentration, absolute value times. And here's the thing. For a strong acid, the percent ionization is effectively undefined. It's gigantic because you're trying to divide by 0. Remember, a strong acid, there's no more HAs. So we don't say percent ionization for a strong acid because you're dividing by 0, so it becomes undefined. However, we are saying this for a weak acid. And rather than do that one, let's use the information we already have. So let's look at the percent ionization of our 2.5 molar HF solution. I don't remember what the A minus was. You guys have it written down somewhere.
0.043.
0.043. So go ahead and calculate the percent ionization again. Absolute value times percent. I just put the absolute values in there if I have it when we do percents. 1.72?
Yeah.
All right, cool. So this weak acid is 1.72% disassociated. All right. Now watch what happens when you change the concentration. We're the same. Oh, I got it my own way. All right. Anyway, HF is association with A plus A minus, X minus X plus X plus X. And then this is this was 2.5. I'm going to dilute it. Okay. So at 2.5, we get to 1.72. And I'm going to get a blue pen, and we're going to dilute it by 10%. And initial, oops, got it all mixed up. And I dropped my thing on my pants. Gross. All right, so initial 2.5 is going to become 0.25, and 0 and 0. This is still minus X, this is still plus X, this is still plus X. Equilibrium is going to be 0.25 now, and X, and X. Does the Ka change based on the concentration of the acid? Does the Ka, the equilibrium acid value, change based on a, no, what is the only thing that changes Ka? Temperature. Good. So, what was the original Ka, or what was the Ka you solved for?
7.24 times 10 to the negative 5.
Negative 5? Negative 4? Negative 4. And it still equals x squared, but now in the denominator, it's 0.25, not 2.5. So now what is the x?
1.8
1.81 times 10 to the negative 4.
1.81 times 10 to the negative 4. Of course, it's molar. And what was the pH of our 2.5 molar solution from previous exercise?
1.37.
1.27. Now, notice what happens when we dilute the weak acid by 10. What's that pH?
3.74.
So of the 0.25 HF solution, our pH is not 2.37. You said it's 3.74.
74.
We diluted it by 10. Remember in the serial dilution when you use strong acids and strong bases? Every time you dilute by 10, you just move the decimal and you change the pH by 1, 2, 3. So you take a pH 2, you dilute it by 10, it becomes pH 3 for a strong acid and strong base. But for a weak acid, that is not the case because you're using this squared up here and you're using the Ka. Is that clear? Muy importante. Next, let's look at the percent ionization. Are you surprised by the number? That making something more dilute increase the percent ionization? What did you get for the percent ionization? I thought you were doing it.
0.724.
0.724 per percent?
Yeah.
Yeah.
Is there actually, is it 0.025 or is it just 0?
No, it's 0.25.
Okay.
Yes.
Wait.
Thank you for doing the math that you actually saw in front of you and not the math that, yeah.
Got small.
Got small.
It's the maths one.
Oh, get out there. Over. Get out. 0072. Okay. Well, it is what it is.
I messed up.
Yes, this number is wrong.
Yeah, I forgot to take the square root of that. It's 0.0134.
Okay, try this again. This number, it's 0. Say again?
0.0134.
134 molar. Yeah, that's more like it.
5.3%.
And
Okay.
then the pH is 1.87.
That's more like it. 1.87? Yeah, all right. So the percentage you said it was 5?
Yeah, 5.36.
5.36%. So again, it's just math. But it's math you don't want to have to do on a multiple choice test or multiple choice question. You have to understand, when you dilute a strong acid, pH changes by 1. Concentration changes by 10 to the negative 1. Or 10 to the first, by 10. When you dilute a weak acid, the pH does not change by 10, or by 1. The concentration does not change by 10. And when you make a weak acid more dilute, the percent ionization increases. How are we doing? A more dilute weak acid has a higher percent ionization. those weird things, just like having to do with negative exponents. That's the hardest part. I think this is why we never went to this far in chemistry 1, but I think this is why they pulled acid base out of chemistry 1. They didn't like all those negative logarithms running around. They're like, I'm afraid. Okay. Anyway, so I guess the experience is percent. Do you feel comfortable going backwards with percent ionization? So if you are given percent ionization and a concentration, you can find Ka. You know what? I was gonna we have time. Let's go over it. Let's do this one. Acetic acid, the AP's favorite acid, has a percent ionization of 0.67% in a 0.3 molar solution. Find the Ka. So, can I erase all this? All right. Leave that up there. Get rid of that. Rice, rice, rice. God loves some rice. And we have HC2H3O2. By the way, if you are doing any kind of equilibrium, remember how I said the process is more important? Put your rice table up there and your equilibrium expressions. Do not shortcut, because shortcuts will cost you points. Okay, so what we need now is to figure out what we have present. Well, the initial concentration is 0.300. Actually, we're going backwards. Find Ka. Yeah, okay. So that's also going to be minus x plus x plus x, 0, 0. This is also going to be 0.300. Because the 0.300 minus x is effectively 0.300, since weak acid, Mr. Byers told me. Okay, what we don't have is this, because normally we get those x values from the Ka. But in this case, we're going to find the Ka based on those values. Is that clear? Where do those values come from? Percent ionization. Because our percent ionization is A minus over HA, which means the A minus is the percent equal to the percent ionization times the HA.
Also times 100, right?
Yes. It gives it to us as percent. So this is going to be 0.0000767 times the HA, which is going to do us at 300. Get teeny tiny. Acid base is teeny tiny. Get those numbers right? 667.3. Yeah, right.
Should be 0.0023.
0.0023. Hi.
Lecture?
I am. Oh, okay. Just give me another five minutes.
Sure.
Okay, so 0.0023, and this is the concentration of the A minus and the H plus. So that's our X right here. 0.0023, 0.0023. Okay. Are you comfortable with this? Okay, so now just plug the numbers in. Because again, we're always going to write our expression. Oops, Ka. We'll do pH later. Our Ka is our H plus concentration, A minus concentration. I'm like, but I can just do the math. It's like, don't just do the math. So 0.0023 squared over 0.300. That's going to give us our Ka. I wonder if this is actually accurate to what it really is. All AP Chem teachers memorize the Ka of acetic acid. It's 1.8 times 10 to the negative 5.
Yeah, it's
Is it 1.8 times 10 to the negative 5?
it's like 1.76.
Cool. All right. Now that checks one box, we found the Ka. The next box is to figure out what the pH is. How do I do that?
Logarithm, negative logarithm.
Negative logarithm of what?
Oh, that's 0.0023.
Exactly. Remember, this A minus concentration is also the H plus concentration because it's a 1-to-1 ratio. Is that clear? So to find the H3O plus concentration, you just use the same A minus. So negative logarithm of 0.023 gives us a pH
2.64.
2.64. All right. Are we all on the same page? How you feeling about this? Feeling good? Okay. Again, kind of a brain bomb. Hopefully we can get Canyon up to speed. All right. Yep. That's more of the same. Aha. This is what I was talking about earlier. A 0.15 molar ammonia solution has a pH of 8.5. Find the Kb. Well, you're going to get the pH, you're going to get the hydroxide concentration and the ammonium concentration from the pH. What are you going to do with the pH to get those numbers?
It's the opposite of whatever you just did.
Exponentiate.
And we're not going to do that yet. We need to find the POH.
Oh, 14.
Again, this is exactly what I was telling you about. They're going to give you an exercise where you need the base information, and they're going to give you the acid information. But you know this, because if the pH is 8.75,
14 minus that.
then it's going to be 5.25. And if you know the POH, what do you also know? You know the OH. How are you going to find the OH?
10 to the negative 5.25.
10 to the negative 5.25. And if you know the OH, you also know the A minus. One more concept after this, and I'll talk to Mr. Tucker. What are these two values?
OH is 5.62 times to the negative 6.
Is that also the ammonium concentration?
No, that should be 1.78 times 10 to the negative 1.
No,
Oh wait, no. I was looking at that as a
Yeah, they're the same.
Yeah.
Because it's a 1-to-1 ratio. So now that we have that, go over here, then the Kb says to solve for the Kb, right? And the Kb is just going to be our x squared over our b, which you said the x is 5.62 times 10 to the negative 6, and our original concentration 0.15. And now you have your Kb. Make sure you double this because it's x squared or squared. And now you have the Kb. Anyone got a number for me?
2.11 times 10 to the negative 10.
All right. All right. Can we get a second on that?
Yeah.
All right. So again, if you have Ka, you have Kb. If you have pKa, you have PKB. If you have PKB, you have KB. If you have PKA, you have KA. You have tons of information. And here's the beautiful part. To link one square to the other, all you need is one of the numbers. So again, if you've got pH, you've got POH. If you've got H3O plus, you've got OH minus. If you've got pKa, you've got pKb. And if you've got Ka, you've got Kb. That's a B. You've got Kb. And you only need one thing to link these two together. What do you think it is? You need molarity. If you have the molarity of the solution, you can link these two together. So if you have anything, Alexa, stop. Alexa, stop. You didn't say 5-minute warning. Weird. Okay. So if you have any of these, you have all four. If you have any of these, you have all four. If you have anything here and a concentration, you have everything. If you have anything here and a concentration, you have everything. All you need is something out of this box to get everything. All you need is something out of this box to get everything. Something out of this box and a concentration gets you all of these. Something out of this box and a concentration gets you all of these. All right, how are we doing? Are you comfortable with this? Canyon, good. We have one concept left, and it's really simple. If you encounter a diprotic or a triprotic, that's a diprotic, that's a diprotic. The most important thing, do not get freaked out, always use a single proton. If you are given a diprotic or a triprotic acid, the single proton is the only thing we care about. It's the only thing that's going to get tested. They might want you to recognize that there's three protons or 2 protons, but they will not test it. Questions? Okay. Bye, Canyon.
Is
Hope
it
you
gonna be on
enjoy
the
it.
test?
I'm sorry?
Is it gonna be on the test?
It is, in May. It's going to be totally on the test in May, and everybody's going to
My students don't care.